Hello? If you're watching this video, you've probably had to measure something before, whether that was speed, or really velocity, length, or time. Any measure you've made has had a unit attached, like the foot, minute, or gram. But these units don't come from nowhere. There is no universal definition of a foot. Instead, all of these units are standardized from actual universal definitions, those being physical constants. And the system all these constants and measurements make up is called the SI. The Standard International System of Units, or SI for short, is a system of measurement defined via physical constants. The core of it relies on just 7 base constants. These units are the second, meter, kilogram, ampere, Kelvin, mole, and candela. What sets them apart from other base units like the volt, newton, or joule is that they use physical constants in their definition. The first base unit, the second, is defined by the rather boringly named cesium frequency delta nu Cs, the unperturbed ground state hyperfine transition frequency of the cesium-133 atom. It's just a specific radiation wave that's always released by a specific action. Every radiation wave has a specific frequency, and that's the amount of periods per second. To use it to define the second, this wave's frequency is set to be exactly 9,192,631,770 Hz, or 9,192,631,770 periods per second. After some math, that makes the second equal to exactly 9,192,631,770 periods of this specific frequency. Now, this process sets up how most of the base units are defined. A universal constant has some value in some unit, and with that, the value of the base unit can be found. The definition of the meter, for example, is found by setting the value of the speed of light, c, to exactly 299,792,458 meters per second. Since the definition of the second is known, you can then find that the meter is the distance light travels in exactly 1,299,792,458th of a second. Each unit from the base units of the SI is derived in the same way. For example, the kilogram or kilo is found by setting the value of the Planck constant to exactly 6.62607015 times 10 to the negative 34 joule seconds, or kilogram meters per second squared. Since the value of the meter and second is known, it can be found out what the kilogram is. You should be able to see where this is going. The charge of a proton is exactly 1.602176634 times 10 to the negative 19 coulombs, and a coulomb is equal to an ampere times a second. Dividing by the value of a second gets the value of an ampere. The Boltzmann constant is 1.380649 times 10 to the negative 23 joule kelvins, or kilogram meters squared per Kelvin second squared. Dividing by the value of a joule, which itself is defined by the kilometer and second, gives the value of a degree Kelvin. The candela is found by setting a specific frequency of light called KCD to be 683 lumens per watt, or candela steradian second cubes per kilogram meter squared. Steradians being simply the 3D equivalent of a radian and thus having a purely mathematical definition. With all of these units defined, it is then possible to derive units from them. For example, take the hertz from earlier. Since some number of seconds can be the amount of time required for one period of a wave, and a hertz is meant to measure frequency, periods per second, a hertz is defined as the reciprocal of a second, x periods per second. Acceleration is increase in meters per second every second, and force is mass times acceleration as defined by Newton's second law, so the unit of force, a newton, n, is defined as kilograms, mass times acceleration, meters per second squared, or more intuitively, the amount of force needed to accelerate 1 kilogram of matter to 1 meter per second over the time span of 1 second. A joule is then the amount of energy used when a force of 1 newton moves something 1 meter. Of course, not just the official SI units are used in everyday life, but every unit used now is defined from them. A foot is 0.3048 meters, a gallon 4.54609 cubic decimeters, and a degree Fahrenheit is 1.8 degrees Kelvin, and so on. All these units are used so often from everyday life to industrial applications and space missions, and the Standard International System of Units lets us define these units precisely against the laws of nature themselves.